Well, probably good afternoon to most of you. Welcome to the ESIP Summer Meeting EnviroSensing session. Today's topic is innovations in EnviroSensing technology and practice. And this session is sponsored by the EnviroSensing Cluster, which is chaired by Renee Brown, Joseph Bell, and myself, with Christina Faust as our student fellow, who is very engaged also in moving the cluster forward. So we all welcome you to our live meeting session, where we've got an exciting lineup of speakers. And before I click out of this title slide here, if you haven't been to our cluster webpage, take note. You can find information, especially our email list information there. You can join the email list and contribute there and exchange information. Students are always welcome. We're very student-friendly working group, so come on in. All right, so with that, I'm going to go ahead and stop sharing my screen here, and we will get into our program. We have two invited speaker groups, and then a set of 4 flash talks, and everyone will be sharing their screen. There'll be a little bit of transition time in between. There are going to be longer Q&As for the invited speakers, and for the flash talks, we'll probably be able to take a single question as folks are transitioning to sharing their screens and their slides. So remember, if you have a burning question for your speaker, one, go ahead and enter it. Feel free to enter it in the chat here in Zoom, and hopefully we can get to it. But if not, get your speaker's contact info and collar them in the virtual hallway later, and continue the discussion. So with that, we're going to go ahead and hand it over to our first invited speaker. And this is actually interesting. There's a group of folks down in Santa Barbara that are working on a cool project, and their PI had some last-minute changes. So we're actually going to have some of our graduate student colleagues come in and give the presentation. So Caitlin, I believe you're leading this one. And so Caitlin Ziegner is from the SWEX project. Probably not going to be able to say the acronym correctly, so you can tell me how you guys refer to that. But this is a really exciting project on atmospheric sensing down in Southern California. So Caitlin, go ahead with 15 minutes or so, and then another 5 minutes for Q&A. The floor is all yours. Welcome.
Great. Thank you so much, Scotty. I'm super excited to be here. And also, I think this is my first online presentation, so I'm excited, a little bit nervous. So just stick with me in case there's any technical difficulties. All right, I think, am I sharing my screen?
Yep, we can see the PowerPoint page, and yep, title slide.
Perfect. Okay, going well so far. I'm going to move you guys over my screen. All righty. So hi, everyone. My name is Caitlin Ziegner. I'm a 5th-year PhD student at UC Santa Barbara. And like Scotty was saying, I'm in a lab group with Gertjan Duin. He is the postdoc in our lab, and our lab is led by Leila Carvalho and Charles Jones. So Gertjan couldn't be here today, and I'm going to give his talk titled Unraveling Principal Mechanisms Controlling Downslope Windstorms in Coastal Mountainous Terrain Using Novel Instrumental Strategies. Now, this research was funded by an NSF grant shown in the lower left-hand corner. And this picture in the background actually shows some mechanisms at work during a wildfire. And I'll get to that in a second, but that's just a teaser of what's ahead. So Santa Barbara is located in California, kind of in the southern central region between Los Angeles and San Francisco. On a typical day, this is what you see. It's gorgeous. You can see mountains, you can see the ocean. There's maybe a couple of clouds in the sky, but overall high visibility. However, occasionally there are devastating wildfires in this area. On the top, we can see the Jesus Cita fire, which was in 2009. And in this case, the fire originated high on the mountain slope and was quickly spread south toward highly populated regions from strong winds coming from the north, so over those mountains. On the bottom, we see the Thomas Fire, which occurred in 2017. Now this ignited closer to Los Angeles, but was spread to the west towards Santa Barbara. And here you see a picture from the wharf looking up toward the mountains where the fire is ablaze. Okay, slight lag. So all major wildfires in coastal Santa Barbara are associated with extreme downslope winds, and these are called sundowners. I'll explain why in a second. Now in this upper left-hand image, we see the topography of the region, which is colored. We have the San Ynez Mountains, which is the main mountain range you saw in the image before. And then you see to the south, all of the roads and the trails in this region. Now, the more dense the roads and trails are, such as closer to the coast, the more highly populated. So we do have some areas in the wildland urban interface, or the WUI, that are extending onto the mountain slopes. And this is particularly at risk during sundowner winds, which coincide with wildfire ignitions. Now, like I said, all major wildfires in coastal Santa Barbara are associated with these winds. In this bottom image, you can see all wildfires that have occurred since the 1970s. Now, most of these ignited high up toward the ridgeline and were rapidly spread south. You can see in the middle here, the Painted Cave Fire, the paint fire, actually crossed some of these major evacuation routes. So wildfires, especially coinciding with extreme downslope winds, are really, really important to understand in this region. What is known about these sundowner winds, and why are they called that? They're called that because these winds onset around or after sunset. There's also high spatial and temporal variability in the winds, the temperatures, and the relative humidity during this event. If you look at the image on the bottom, the color indicates the relative humidity during the Jesucita fire. The red colors are located in the eastern regions, and this means that there's very low relative humidity. Whereas if we look in the western regions, we have higher relative humidity. We also can see that the winds have more of a westerly component in the regions to the west. However, in the eastern regions, by Santa Barbara, Montecito, the winds are more northeasterly, so we have a lot of spatial variation. Sundowners are most frequent in the spring months, however, they do occur year-round. Finally, we sometimes observe east to west progressions of the onset. However, sometimes the onset occurs simultaneously on the mountain range. So this just goes to show how each one of these sundowners has different, per se, flavors and different mechanisms at work. One study by Jones et al. In 2021 shows that there's evidence of eastern and western sundowner regimes. This upper left-hand image is the western regime. The colors are indicating the wind speed, and the vectors indicate the wind speed as shown by the length and the dominant wind direction. Now with the western focused sundowners, we see the maximum over here, this little red pocket, and this peaks around 19 PST or around 18 PST. However, during these eastern focused sundowners, the wind speeds are most strongest on the slopes above Santa Barbara and Montecito, and the maximum time of maximum occurrence is around 23 PST, so closer to midnight. So this just emphasizes how variable these events are spatially. There are three ingredients for downslope windstorms and for sundowners specifically. First, we need a large mountain barrier. So in this case, we have the San Ynez Mountains. Second, there needs to be sufficient airflow across the barrier with a stable environment at play. And finally, there needs to be some sort of mechanism that is reflecting mountain waves. This can be a critical layer, this can be shear, or this can be an inversion near the mountaintop. And all these relate to upstream profiles. So in this case, what is happening to the north of Santa Barbara that is influencing sundowners? Here's an example that we can actually see some of the mechanisms at work. So imagine you're in Montecito to the east and you're looking west. So we have the mountains on the right-hand side of the image here. This was taken during the T fire in 2008, when there was an ignition near the ridgeline and a strong sundowner was pushing the fire to the south toward highly populated areas. We can actually see what's called a hydraulic jump. So we see this kind of wavy pattern that's propagating the fire and spreading the fire to the south. And this is important, especially during wildfires, because this can cause ember transport, so we can have spotting ahead of the fire, which represents a challenge for firefighting and evacuation strategies, and also is very difficult to simulate in fire spread models. Some additional challenges are the upstream conditions for the San Ynez Mountains. They're highly variable. And by that, I mean to the northwest, we have the San Ynez Valley. And to the northeast, we have the San Rafael Mountains with peaks exceeding 2 kilometers above sea level. So we have different conditions, especially given we have these east and west sundowner regimes. Additionally, the Santa Barbara is located right next to the Pacific Ocean and the Santa Barbara Channel. So we have a marine boundary layer that is spatially and temporally variable. Like I was saying before, we have evidence of east and west sundowner regimes. And also there's only a handful of remote automatic weather stations and automatic surface observation stations, so land-based stations that are trustworthy. There is a wind profiler that was installed in 2016 at the Santa Barbara Airport that can be used during sundowners as well, but that's fairly far away from the mountains. So typically we rely on numerical simulations to understand sundowner processes on both spatial and temporal scales. In April 2018, we had the SWEX pilot experiment. So that's the Sundowner Winds experiment. During this time, it was just one overnight period. We took radiosondes every 3 hours at a location that's in the middle of the San Ynez Mountains, in between the cities of Goleta and Santa Barbara. The goal of this one-day field campaign was to evaluate critical mechanisms for the lee slope winds using only observations. Like we were talking about before, the results showed remarkable spatio-temporal differences in the lee of the San Ynez Mountains. Here's one image that was taken when we put all of the radiosondes together. Now in this image, the shading is the wind speed. The x-axis is the time of day, where the blue lines are indicating a launch time of a radiosonde. And the y-axis is the height in the atmosphere. So as this balloon is launched, it goes up through the atmosphere and collects a profile of the winds. And then we can put it all together to see how winds were changing over time and with height. So what we gather from this graph is that there was a nocturnal jet about 17 meters per second, around 21 PDT. We can also see that there was a re-intensification closer to the surface around 3 in the morning. So this is showing at this one location how the winds are varying over time and over height. Now, the main reason I'm here to talk to you today is to talk about SWEX 2022, which is planned to take place from April 1st to May 15th next year. This is a very collaborative field experiment with 9 institutions as listed on the bottom of this image. In this field campaign that lasts about a month and a half, we will install 19 weather towers, have 6 LiDARs, 3 wind profilers, 4 ceilometers, and 1 SODAR. And with all this instrumentation, we plan to use 11 observation periods, so 11 sundowners during this 6-month period to study. So during those selected times, we will launch radiosondes, or also called weather balloons, every 3 hours and at 4 locations. So in the SWEX pilot, we launched weather balloons every 3 hours at 1 location. So this is expanding our spatial scale. There will also be 2 mobile trucks enabled so that we can look at the characteristics that are modeled and look at specific items and characteristics and mechanisms during sundowners. Finally, we will have an aircraft that will take LiDAR and also do some drop-ons. So they're going to drop a meteorological package and capture the atmospheric conditions from the top down. We'll also be collecting in situ obs during this entire time frame. For more information, you can go to this website here, and I'm happy to share this presentation after. The objectives are SWEX is to elucidate atmospheric mechanisms that control sundowner winds. Like I was saying before, we typically use models a lot because of the limited availability of observations in this area. So by using all of these additional instrumentations, we will be able to more fully understand sundowners and their mechanisms. So we're going to use the instruments for about 6 weeks and look at especially mountain waves and wave breaking. We'll look at the relationship of the valley boundary layer upstream, so the valley to the north of the San Ynez Mountains. We're also interested in looking at the marine boundary layer, so the areas that are south of the mountains. And the overall goal of this is to improve sundowner forecasting, which will in turn improve fire spread modeling and increase resilience to wildfires. Here's some of the instrumentation we'll be employing during SWEX 2022. On the left-hand side, we have surface flux towers. These measure moisture, winds, and temperature only at the surface. You can also calculate some turbulence parameters. Next, we have the microwave radiometer, which captures the vertical profile of the atmosphere and the thermodynamic structure. And these will be placed upstream of the San Ynez mountain range, so in the valley and in the mountains. Next, we have the wind profiler. This captures wind above the instrument, and it can go 5 to 8 kilometers above sea level or above the level that is installed. And finally, we have radiosondes, which are these weather balloons on the far right-hand side. These collect data such as temperature, humidity, and winds. And like I said before, we plan to launch these every 3 hours at 4 locations. Finally, we have some instruments that revolve around remote sensing. We'll have 5 LiDARs on the lee slopes of the mountains spaced out. Hopefully we'll be able to further understand these east and west sundowner regimes from these, if not understand more mechanisms. There will be some mobile trucks as well as the aircraft, which I mentioned before. So definitely including remote sensing instruments in this analysis as well. So that's all we have. Thank you very much, and I hope that I explained that fairly well. Gershon wishes he could be here today, but he can't. So I can try to answer any questions you have, and if I can't, then please feel free to email Gershon or Layla. Thank you.
All right. Applause for Caitlin. Caitlin, you did a great job filling in there for your lab.
Thank you.
Actually have, looks like we have more than 5 minutes, 7 minutes for questions. So floor is open. Anyone have a question or two for Caitlin? Silence on the line. So I have a question. That's a lot of instrumentation, and getting, fusing the data is going to be pretty interesting. I don't know if you can answer this or not, given how big the project is, but do you have a separate team whose job it is to do data quality control and fusion, or is it every instrumentation team for themselves?
Yeah, that's a really good point. I don't know the answer to that. Layla might. But yeah, as you can see, so many organizations and institutions are involved in this research. So I'd imagine there has to be some data quality control occurring. I'm not exactly sure who's involved or if everyone can just go for the data as they wish. If you would like to know, I'd probably email Layla regarding that question.
Okay, other questions?
Hey, it's Steve Young, and Caitlin, great job with the
Thank
talk.
you.
I can't believe that was your first online presentation.
Thank you.
Really well done. I'm sure that you've talked about using drones. So it's sort of a two-part question. One is drones, and part two is, are you kind of exploring possible citizen science components to maybe fill in some additional data?
So the first question about drones, I'm not sure if we've looked into drones. That is a really good point, though. I'll definitely mention it to Layla and ask her, because I'm interested in that now too. I do know, because we have the Santa Barbara Airport extremely close to all of this, even when we were launching radiosondes with the SWEX pilot experiment, we had to call every single time and get verification from them that it's okay. So I'm not sure if it's just the drones would be too complicated to work with them on it or what. But that is a really good point about utilization of those. And then your second question, I'm sorry, I forgot.
No worries. Discussion about citizen science angles, maybe some sort of deployable instruments that might help fill in some additional ground-based observations.
Yeah, I think that'd be a really cool aspect as well. I'm not sure for this experiment if we have looked into that. I actually recently published a paper about using the RAWS and ASOS stations to create an observational climatology per se. And one of the comments about that was using other stations like in people's backyards and such. And some of the questions and issues with that is, are they following the regulations that scientists are and these organizations are, or are they kind of going off track to the point where the data would be misleading per se? So I think that may have dissuaded us from using citizen science, but it still definitely could be an option if there were strict guidelines and protocols, I think.
Sure. Well, thank you.
Thank you.
More questions?
I have one. So given where you're at in your experience with the project, what would you do different in, or how would you modify the planned sensor implementation and sensor deployment? What would you do different next time?
I think the thing that I would do different, if I were Layla or anyone else high up in organizing this, is connect with the graduate students maybe a little bit more and reach out when needed. So I know that there have been many discussions with Layla, Charles, Gurjan, and more people about exactly where to place all of these stations and all of the instrumentation. And I'm sure if I asked any of them, they'd be happy to explain it to me. But there were at points where I'm not exactly sure why some of them are placed where they are versus in a location maybe a couple kilometers away. So I'd probably say just incorporating more aspects and getting the information out about station placement in a region where the spatial placement is extremely important to what you will record.
Excellent answer.
Thank you.
We have time for one more question. Okay, so what happens if you get an ignition when the experiment's running? What's the plan?
Oh, goodness. Oh, stay safe for sure. The National Weather Service in Los Angeles, Oxnard, works extremely close with us, with Layla, Charles, and the rest of us at UCSB, and probably more research that I don't know of. So they rely on us as much as we rely on them to forecast sundowners. So I think if there's a risk of an extreme sundowner, they'll have the appropriate measures ready to go. So as far as the Santa Barbara County fire goes, there was a fire that ignited called the Holiday Fire. I think it was 2019. And the National Weather Service and UCSB was like, yo, there's gonna be a very bad sundowner. We don't know if there's gonna be an ignition or not, obviously, but if there is, have everything ready to go and extinguish it. And sure enough, there was an ignition that was within the wildland urban interface, and the fire department was on it and put it out very, very quickly. So I'm hoping that with all these collaborations that we already have in place, we can work together to keep not only us safe, but also the rest of the community.
Okay, thank you once again, Caitlin.
Thank
Great
you.
job. And we're going to turn it over to our next invited speaker. So this will be Christelle Valentine from HydraMed. And Christelle, if you're there, there I see it. Okay. Glad you could make it. Welcome. And you have approximately a total of 20 minutes. We're on time, so no worries, no pressure. And you're going to talk a little bit about some R&D in a private-public partnership with the USGS on Internet of Things. So I'm really interested in this topic, and we're glad to have you. So Christelle, the floor is yours.
Great. Well, thank you very much. Appreciate the introduction. And I'm going to go ahead and share my screen. Okay, and share. Okay, do you see my screen? Perfect. Very good. Yes. So thank you very much for inviting me to present on the topic of improving data availability and really looking through the lens of innovation to accomplish that task. So I'm Christelle Valentine with HydraMed, currently based in Colorado. and I'm the Director of Marketing for our hydrology vertical. Before we dive into the topic of innovation, I just wanted to spend a few minutes to help frame and orient the audience here on who HydraMed is and in our role in innovation. So HydraMed is a developer and a manufacturer of solutions that are focused on hydrology, meteorology, and solar energy. So our solutions comprise of hardware or software. We have 8 brands that are within our product and solution portfolio. Those brands are listed in the slide here. You may be familiar with a few of these brands that are focused on technology that's responsible for monitoring environmental water quality or hydrology solutions, such as the OTT brand or Sutron for data collection, Luft for weather, or Aquarius for software solutions. So let's take a minute here to, just one moment, I am having a presentation malfunction. 1 minute here. For some reason it's saying my picture cannot be displayed. Ooh, just 1 minute. Okay, so we are going to improvise and we're going to do this on the fly a little bit. When I was rehearsing the presentation, everything was working just fine, and that appears not to be the case right now. I'm going to unshare my screen just for 1 minute so I can readjust the presentation. So bear with me here. My apologies for this technical challenge that we're facing here today.
No worries, take your time.
I'll jump in, everybody. This is Joseph Bell. Turn my camera on. Yes, so this was, it's great to have Christelle here. Sorry for the trouble there. So Christelle and I met through USGS, and specifically, we met through the Next Generation Water Observing Systems program. And it's been quite a great relationship in the sense of learning together, learning how to connect the business side of the world with USGS operations, and USGS operations with the larger business side of the world, as well as some of the smaller companies under that. Chris, I'll just jump in anytime you have it. But one of the things that I find very rewarding from this section specific is that as somebody in the USGS, we are looking for innovative solutions, and we're looking for those on the fly solutions, but we're also looking at tried and true. So when we look at things from the research perspective and we look at things from the cutting edge, we often go back to academia side and try those risky cutting edge stuff. And on the other side of it, where we need the tried and true, we turn towards the manufacturers with their manufacturing of scale and the such. And so being on the R&D side of the house, I get to scale the fence of what is a product and what is a prototype. It looks like you're ready to go. And that's really where Christelle and I have a relationship professionally between the two of us.
Great, well, thank you, Joseph, for ad-libbing there. So I found a solution. I closed out the presentation and reopened it, and that fixed it. So it's kind of one of those classic hit the restart button. So thank you for bearing with on that technical challenge there. Yeah, so talking about innovation, just to give you an idea of the types of expertise that we have in-house and the type of solutions that we're working to innovate upon, it really does span across a broad range of hydro and met applications. So in the top row here, we're really looking at our meteorological applications, solutions for long-term, continuous, highly reliable, highly accurate meteorological and climatological data, and the full solution to get that data back from these really harsh remote environments and then back into your offices, into your universities, into your labs. Additionally, looking at technology that is used for renewable energy. In the picture here, there's an example of a solar panel farm and pyranometers that are used to detect the solar radiation, and that helps to determine, is there soiling that's occurring, accumulation of sediment, of debris on the solar panels that could affect efficiency. A few of the other types of applications on the meteorological side include road and runway weather. So think about more of your event management. Do you need to apply any sort of de-icing treatment to the roadways to keep motorists safe, or temporarily shut down runways because of adverse weather? And then also agricultural meteorology for things like disease monitoring, looking at wilting of leaves to really help produce data that can be used for managing crops and protecting viable crops. Now, my area of focus in both studies as well as within HydraMed is more on the hydrology side, focused on surface water quantity, and really looking at how we can continue to evolve and innovate solutions that are driving the data that's needed for water resource management. So this is a station that would be collecting water level, flow velocity, precipitation. So again, really, looking at that time series data set that can be a foundational component for a lot of the planning and a lot of the modeling. Contrasting that with the next image, which is around flood warning, which is again more about that sort of event-based management, where data is needed instantaneously to make critical decisions that can help save lives and property. In addition, there are kind of two other areas of focus: groundwater. So groundwater, both in terms of how much water is there, looking at the overall levels in groundwater, and then also environmental water quality. So from your streams, your rivers, and your estuaries. So I thought this context would be helpful to kind of frame a little bit about who HydraMed is and where we're focused. Now, when we look at investing in the future and providing reliable data that can be used for whether it's predictive models or for critical decision making for events, it really is about how do we take our experience across our brands and our solutions, in our experience, not only in the application or in the development process, in the research and the development, but how do we also take that expertise in manufacturing solutions that can scale, that can be manufactured in not only 10 units or 100 units, but 1,000 units, and how do we consistently provide those solutions that are meeting the quality requirements, the delivery requirements, having the right inventory to offer these solutions. So there's innovation within the process, and also innovation in terms of how do we continue to provide the local support and really be there for questions, be there for feedback from the customer base to really continue to drive innovation forward. Now, there's two boxes here on this slide that I want to really park on and talk more about. Those two are around innovation and innovation specifically by partnering with customers. So at the beginning of the talk, it was introduced, how do we take a private and a public partnership, and how do we kind of evolve that and drive that forward? Well, I wanted to start with an example of a product that was kind of start to finish and how this worked, and then go into another project that's more underway. So when we look at how do we innovate technology, and how do we do so by partnering with our customers, it really for us starts extremely early on in the development process, actually before the engineering team is even involved. It really is about understanding the problem that we're trying to solve. And how we go about doing that in the case of this particular project, which was for a water level system, was to actually go in the field, to work with the scientists, to work with the field techs, to spend a day in the life of, to do the job, to deploy the sondes, to, check the devices, to install them, to understand how that process works, that workflow, not only when you're in the field, but also when you're coming back and tracing that data back into the office. How is it coming into a gateway? How is it coming into a server? How is that data then being pulled out of that server or gateway? Who's doing that? What is it that they're trying to accomplish with that data? What decisions are they making? What QA, QC are they performing? And in understanding that workflow process, in observing it. And within that observation process, we're able to understand compensating behaviors, challenges, frustrations, where are there opportunities to innovate, not just on, more accuracy or reducing the time, but how do we really make a solution, fit to the job that's to be done? So we can identify both the implicit and the explicit needs. And we do this across, in this case, the data transmission journey. And when we looked into this project and we identified what some of these ultimate needs were, we really saw that it was around, how do we reduce the overall data acquisition costs? This is a device that's out in the field, remote location, complete system with a battery, with an NB-IoT modem collecting water level. How do we reduce the total data acquisition costs? How do we do that and get the information that's needed back in the office when it's needed? So we looked at, ways to innovate around the total solution to really reduce the number of components, to bring in some of that newer technology that was coming up in the market that we were seeing in telecommunications and leveraging, in this case, NB-IoT. Also, when we looked into some of the key problems that we were trying to solve in this case, it was around how do we ensure that we're providing that continuous time series data and really reducing data gaps and reducing the likelihood that there would need to be a field visit. Well, what we saw with this type of solution is, again, it's kind of remotely installed, is that, and it being a full system, that power could be a challenge, and the device is performing a lot of activities. It's taking a measurement, it's collecting it, it's storing it, it's transmitting it. It may be transmitting alarms. The user may also have remote communication where you need to go back and talk to the device. Maybe you're curious what's the instantaneous reading, or you want to check something in the data, if you're performing QA, QC. So having that two-way communication, that can pull on the device a lot and in terms of its power budget. So it was real important that the innovation here pushed on, in this case, that intelligent power management to really optimize how such a complex device with all of the, activities that it had going on, how it could be installed remotely for a very long period of time without any sort of interaction, especially the exchange batteries. So these are just a few examples of how, with partnering with our key customers at the beginning of the development process, and then also going back and working with them through concept testing and being able to go and showcase, here's what we're thinking, here's our solution and how we're going to solve this problem. How does this fit within your workflows? Was really a great example of how we can innovate collectively. And we did so really in the context of it being a very open dialogue and open exchange, and that was possible through entering into non-disclosure agreements and being able to really, have those open discussions and those open dialogues. So that was a great example of kind of a start to finish process here, where we have a complete solution that we partnered with our customers to help design and engineer. Now I'd like to move on to another example, which is around the Sutron Hotlink and the X-Link 500 data loggers. So a data logger in this case is really, I like to make the analogy that it's like the heart and the brain of a measurement station. It's the unit that is triggering the sensors to take a measurement. So imagine like a USGS station that's measuring water level, maybe it's measuring water quality or precipitation. It's a data logger in that type of station that's triggering the measurement, saying, hey, sensor, wake up, take a measurement, send that measurement back to me. I'm going to then store it, do any sort of processing, and then I'm going to package it and I'm going to transmit it out when it's time. So these data loggers are really core to the measurement station. And what we've seen is that many customers have and are currently modernizing the type of data logger that's being used. And one of the key things about this type of technology is how do you also, quote unquote, future-proof it? How do you make it useful and applicable so what you've put in your measuring station today is going to enable future upgrades, future retrofits, future capabilities, where you can solve problems around connecting new and different types of sensors. So how can we solve the problem about leveraging the existing logger that's in the field or is about to be put in the field to maintain or increase data availability? I'll give you a few examples. So in the case of the USGS, if they're looking at collecting information from newer different types of sensors, maybe it's a wireless sensor. In the context of IoT, it could be like a sensor that's remote, wireless, and transmitting LoRaWAN. How do we then leverage that existing infrastructure that's in the field, the existing technology, to capture that information that's, instead of coming across the cable, now coming across wirelessly? How do we integrate it? How do we package it? How do we transmit it? So let's take another example. If you have a sensor that's maybe collecting a lot of information, how do you now package that information from the sensor side in the data logger and transmit it back through the normal mechanisms of piping data back to your data collection server or your data collection software? So these are all kinds of problems that we're now trying to solve through utilizing innovation, partnering with our customers to really understand what are the key opportunities to leverage existing technology. How do we leverage something like Python scripting to now assist with collecting information from new or different types of sensors? How do we leverage those scripts to internally within the data logger itself to process that information, to repackage it so that it can be easily transmitted and integrated into the existing receiving infrastructure?
1 minute.
And another example would be, when we think about transmitting sensor data using new and different types of telemetry, telecommunications is not standing still. We go from 3G to 4G to 5G. There's different types of satellite communication. There's Iridium, there's the traditional GOES satellite communication that's being used. But how do we think about integrating in those different types of telemetry, again, to ultimately work as much as possible with the existing standard work that's been put in place? These are the type of areas where early discussions are really paramount to understand and to collaborate, with HydraMed on the private side, and then with our customers, which are often on the public side, and really to set up those discussions, similar to the example that we just saw, to set up those discussions in a way where there's, a cooperative research and discussion around how to go about solving those problems in the context of it being, an agreement and a framework that facilitates those conversations in a type of non-disclosure environment. And that's the great opportunity that we continue to see as we look towards the future, and we look to future collaborations with key customers such as the USGS. How do we continue to work together to solve these problems and to embrace the new and the different, but with a high leverage factor? That's what I'm super excited about. Joseph earlier mentioned that he was excited about that as well. But that is a great opportunity, and it really is an example of how, as a manufacturer and a developer, we can play a role in helping to drive innovation, but in concert with the greater goal in mind.
Awesome. Thanks, Christelle.
Excellent. So I have, I think that was the last slide in my presentation deck. So So I will go ahead and open it up for any questions.
Okay, we have time for one question for Christelle. Otherwise, type it into the chat. Maybe it can be solved while we're going to the flash talk. So any questions for Christelle? We got one. Okay, I'm going to go ahead and move it on to the flash talks. And I have some questions, but I'll probably type them into the chat. So keep an eye on that. So we are going to move to Stephanie Schmidt, who is from the Andrews LTER. Stephanie, are you there?
Yep.
All right. Floor is yours. I'll start the timer and I'll say something if you want a 1-minute warning at 7. And then hopefully we'll give you a chance to answer one question as well.
Okay, great. I will try to share my screen here. All right. Okay, is that in presenter mode? Great.
Yep, looks good.
Okay. So my name is Stephanie Schmidt, and I'm with the U.S. Forest Service and one of the data managers at HJ Andrews, or HJA for short. HJA is located in Oregon, and we are administered cooperatively by the Forest Service, Oregon State University, and the Willamette National Forest. And we're also a member of both the Forest Service Experimental Forest and Range Network and the NSF-funded Long-Term Ecological Research Network. Today I'll be talking about GCE Data Toolbox for MATLAB and how that fits into our climate data workflows at HJA in as much detail as 8 minutes allows. And my colleague, Adam Kennedy, is our GCE Toolbox manager and expert, and also helped with this presentation. We collect a lot of different data at HJ Andrews, but I will focus on our climate data program. And to give you some context about the scope of our program, we've been recording climate observations since 1949. And we currently have 18 active climate stations where we collect up to 12 different parameters, which are listed here on the slide. And we also have hundreds of distributed sensors like hobos placed around the forest. And we process and publish this data on the HJA website, as well as the Environmental Data Initiative, or EDI, repository. And with such a long history and often with limited resources, we've been challenged to scale our technical architecture and tools to keep up with an expanding network of sites with widespread sensor deployment, which is generating a large volume of high resolution data that needs to meet or exceed our historic data quality. And GCE Toolbox is one tool that's really helped us to automate some of our climate data QA, QC, and metadata management. So GCE Toolbox is a software framework that integrates environmental data processing and QA/QC with metadata capture, creation, and management. It was developed by Wade Sheldon at the Georgia Coastal Ecosystems LTR project, hence the GCE. And it's a free add-on library to MATLAB. And it generates structured data files and metadata for archive, which is now a mandate for a lot of funders and publishers. And you can add import filters and metadata templates and build some custom automated processing workflows using interactive GUI forms and a function library. So GCE Toolbox has some nice features which can be used for end-to-end data management, and that includes raw sensor data import, rule-based QA, QC, and flagging, gap filling, resampling and summarizing data, such as calculating hourly means from 5-minute observations. And you can also join and merge data sets and create visualizations. And now we'll talk about how we use GCE Toolbox at HJA. At a high level, our climate data workflow has 3 steps. We retrieve raw sensor data and prepare it for GCE. Then we use GCE for preliminary QA/QC and metadata management. And then we perform additional QA/QC and generate additional metadata on the GCE output before we consider it final and publish it. So we aren't using GCE for end-to-end management, but fitting it into parts of our workflow. So in the first step, data retrieval, which I have highlighted here, there's a few different pathways that the raw sensor data can take in preparation for GCE Toolbox. Our climate stations are either on telemetry or require manual data collection, and our distributed sensors also require manual collection. Our raw telemetry data is prepared using Campbell LongerNet software, and our manually collected data is prepared with custom scripts. A lot of those are in Python. We use Campbell LongerNet database software to import our climate station data to SQL, and our distributed sensor data is stored on a file server. And in this step, we are also using GCE to pull in reference data from regional climate networks like SNOWTEL for cross-site comparisons and data verification. And a great thing about the MATLAB environment is that it's integrated with languages like R and Python. So you can work with GCE and your custom scripts in one environment, which really helps to simplify data management. So our GCE processing is started by a basic task in Windows Task Scheduler, and we run that weekly on our highest resolution data. And GCE Toolbox runs 3 scripts, which we call fetch, process, and harvest. And for our climate station data stored in SQL, the fetch script runs a single dynamically generated select query, which is integrated in a function call that processes the data by station. For our distributed sensor data, the fetch script starts a collector function and retrieves and batch processes the data on the file server. The process script sets all of our constants, our file paths, our import template, and calls the harvest script. Loggers at the same station can share the same harvest script, and that is executing QA/QC, including a flagging and unit conversion. And when the GCE run is complete, GCE is outputting 5 different files, which are down under the output section there. That includes XML, CSV, HTML, MATLAB, and PNG image files. And that is saved to a file and a web server at OSU. And we publish those outputs in a provisional data portal on the HJA website. Now, this is an iterative process. The GCE outputs may require updates and changes before they're considered final. And some of these changes might include adding additional records, changing attribute names, or changing some of the flagging rules. So the data managers communicate about these changes. GCE is rerun on demand, and then we share any metadata template changes.
1 minute.
Great. So when no further changes are necessary to the GCE output, we start our post-GCE processing. And that includes some data restructuring, as well as resampling and summarizing some of the high-res data to hourly or daily resolution for some parameters, doing visual checks, and just making sure that flags were applied appropriately. And when we're all finished, that gets published to the HJA website, as well as submitted to the EDI repository. So to summarize, we handle a lot of data in various formats, and while we don't use it for end-to-end management, GCE Toolbox fits in really well to our workflow and has provided a lot of value and time savings in our processing and metadata management. And because I know we're short on time for questions, I've included my email address and Adam's as well, and provided the website, the official website for GCE Toolbox, which has a lot of great training and documentation.
Awesome. Thanks, Stephanie. Good job.
Thank you.
We're going to go ahead and move to John. And while he's setting up, we'll take one question for Stephanie. So if you want to, there you go. John, go ahead and bring your slides up. One question for Stephanie. Going once, going twice. Okay, catch her in the chat. Keep an eye on the chat there, Stephanie. There's a little bit of discussion going on there. John Porter, you're up next. Virginia Coastal LTER. Go for it.
Okay, hopefully I've unmuted there. One of the questions that I sometimes think about is, how much should a sensor station cost? I've worked with a lot of stations that cost thousands of dollars. They really good stuff. But for some places, wouldn't it be better to have stations that cost tens of dollars instead? So this talk is about using some hobby level technology that's not normally associated with science. Now, most of you, many of you may already be familiar with this stuff. Certainly, there are many middle schoolers and high schoolers that are very familiar with it as well. So let me get that. Yeah. When I talk about sort of low cost, this is a more or less randomly picked one off Amazon.com. This is a typical hobbyist starter set with a number of sensors, including distance sensors, acoustic sensors. I think there's some temperature sensors in there someplace. There's electric motors for doing robots. Everything you see on the screen here, $59. Well, 60. The microprocessors that are typically used for this, and there are others as well, are Arduinos and Raspberry Pis. And each one of them comes in a number of different models, but typically their cost is going to be sort of in that, well, certainly less than $60 or $70, and typically a lot less than $60 or $70. Now, these devices are designed to be able to be hooked up to sensors and to be able to do other things as well. This is just sort of a little quick comparison of the two. Arduinos are really much more about sensing. They've got limited memory. You basically program them with a subset of C. You do the programming using a program running on your computer, and it's got both inputs for digital sensors and also for analog sensors. And it runs on fairly low power, so typically around, let's say, around a 10 milliamps, which would be 1/100th of an amp. The Raspberry Pi, on the other hand, is actually a full-fledged computer. You can see in the picture in the upper right-hand corner there that we're talking about something that's got a GUI interface. It's got internet support. It's got Wi-Fi potentially, depending on the model. It's got USB ports. It's got a place to hook up a camera so that you can get high-speed video out of it. Now, that comes with a cost because it's going to require about 10 times as much power. It's still, under some circumstances, just 1/10 of an amp, but that's still more power than you would typically want there in a field logger. There are also some useful things that they don't have. Okay, first of all, both of them lack real-time clocks. So if they ever lose power in the field, they have no clue what time it is. And that, in the case of the Raspberry Pi, it gets its time for using the network time protocol over the internet. So if it's not connected to the internet and it boots up, it does not know what time it is. Similarly, the Arduino does not have a built-in clock. That said, you can add real-time clock to both of them. That's in the upper right-hand corner. There's a little module that does that. And then in the case of the Raspberry Pi, it doesn't have any analog input ports. It can deal with digital sensors, but not analog sensors, unless you have added extra hardware to it. Now, the Arduino doesn't have a SD card for data storage, but you can get a shield. This is a shield down in the lower left that just fits right on top of the Arduino and adds that SD card to it there. There are also specialized versions of a lot of this hardware. This is a Arduino. It's a specialized version that does have that real-time clock built in and does have the SD card storage and has a place to mount radio connection cards that can include some of the low-rock hardware that we'll hear about later. It's much more designed around that. There's lots of other sort of specialized versions out there. Now, that's the microprocessor side. There's also lots and lots of hobby grade sensors, and many of those are also fairly inexpensive. You can see here that if you want to measure temperature, they've got 80 different sensors to choose from. Now, many of those are actually going to have the same underlying sensor and so forth. But as you can see here, there's just lots of different kinds of things that you can measure, and there are also lots of different sensors for doing that. Many of those sensors are going to be fairly inexpensive. You can get some that are expensive. If you want a LiDAR sensor, yeah, it's going to set you back $150, but a soil moisture sensor only sets you back $695 or $595. Now, is that a sensor that you're going to deploy and use for year after year? Probably not. That one probably has a limited lifetime. Also, not all of the sensors are going to have the levels of accuracy that you might want for all questions. But there are also lots of scientific questions that don't actually require 5 decimal places of accuracy. And then also, the Arduino and Raspberry Pi can also work with high-end digital sensors. I've got some sensors that cost, $2,000, and they communicate using SDI-12. Well, the Arduino and Raspberry Pi can communicate with SDI-12 sensors, so it is possible to do sort of a hybrid system. Now, some things that I've worked on are just using Raspberry Pi for a temperature monitoring system that basically provided real-time web-based graphs of the temperature. I've done things like using a Raspberry Pi as a logger for JSON data coming from a consumer-grade meteorological station. These things are really good at doing sort of robotic things. You can make it so that they don't just listen, but they actually change things. And then shown on the right is basically a little distance-based ultrasonic sensor that's attempting to measure the water in a well there, and then just a data logger there. Now that one I'm still wrestling with because there's some multipath issues with just how big a tube do you need to have and that sort of thing. So not everything works instantly and immediately.
1 minute.
1 minute? That's, I basically just sort of given here when I tend to think that it may be better to go the Arduino route versus the more conventional, expensive data loggers. And a lot of it has to do with how long does it need to be out there and how likely is it to be destroyed? I mean, there's some places you really do not want to put $2,000 worth or $10,000 worth of sensors. And also, since the microprocessors here, the largest ones are about the size of a playing card, it's a lot easier to make that inconspicuous. But if you really are needing sort of state-of-the-art accuracy, if you need to limp by on the smallest of power, available power, then maybe the expensive data loggers. This is not a either or. It's a situation of where you can use both of these in combination with each other. And I'm not encouraging you to just sort of pitch all your expensive systems. We just saw a really excellent talk on a system that I don't think is inexpensive, but it's really good. But it's also possible that for some shorter term things that maybe that inexpensive route is sort of a way to go. And the link to the presentation is there if you want to hit the QR code. There you can look back at all the details I've missed.
Okay, thanks, John. Great job. All right, we're going to transition to our next presenter. So Justin Rubalcaba from Montana Tech is going to talk to us about some soil sensors they're working on, a project up there. Justin, it's all yours. I'll let you know 1 minute.
All right, thank you. And it's funny, John's presentation was actually a very good intro to mine because it uses a lot of the same ideas. So we'll get going here. All right, so yep, like I said, my name is Justin Rubalcaba. I'm a senior undergraduate student at Montana Tech, and I'll be presenting our high altitude soil testing device that we've been developing. This has been developed as a collaboration between the environmental department, biological sciences, and electrical engineering department. So this is a continuation of a project initially developed by Jamison Ellers, who's now a graduate student at our college. What I've been working on is taking his rough prototype and refining it, kind of characterizing the sensors. And yeah, so the whole idea with this device is we want it to be able to measure temperature, soil, and humidity in remote and difficult to access areas, such as the periglacial pattern ground up in Goat Flat, which is an alpine area that's only accessible maybe a couple months of the year. So current sensing is done by going up there, burying a sensor and then leaving it, and then going back and basically collecting the data the next year. So our goal is to be able to get semi-real-time data. So we've included a satellite modem on our device that can transmit short burst data over the Iridium satellite network, so that we can get more real-time data rather than every year. We can get it, daily, basically. So here's just some of the components that were used. We use the Rocket Scream Mini Ultra Pro, which is number 2 there circled. And that is kind of like John was saying, that's the microcontroller that it powers pins up and down, provides the power management of the system, because obviously we want this to be out in the field for, the goal is multiple years. And it also does have a real-time clock built into that one. So the Rockblock Mark II satellite modem there, circle number 1, that is what actually does the transmission. It has a lot of built-in, there's built-in libraries that we can use through the Arduino that do a lot of the heavy lifting as far as the coding goes for us. But there are limitations, as we're only able to send up to 350 bytes of data per message. And we also do have an SD card reader with an industrial rated SD card, so that we can log more verbose data on the device in case there's a sending failure, or if eventually when the power does die, we'll still have a physical copy that we can go retrieve. So a little bit more, we have the Sensirion SHT-10 sensors. We use 4 of those. Those are up in the top corner there. They measure temperature and relative humidity, and they have a permeable casing so that to keep the sensor itself protected. We're using lithium thionyl batteries. We use 3 of those. And one of them directly powers the Rockblock, and the other, it directly powers the Arduino, and the other 2 are used through regulators to power the Rockblock and SD card. For protection, we have a NEMA case with IP68 rated cable glands right here. And that's just to keep water, because this will be buried basically up to the clear cover. It still needs to be able to see the sky to be able to send it satellite transmission, but we want it to be as protected as possible. So a lot of my data that I've been taking this summer has been to characterize the sensors that we're using. So my first test was just to compare to publicly available weather data, just to see kind of a baseline if the sensors were worth continuing to use. And as you can see, the green line there on the plots is the publicly available data, and the other lines were the sensors. So you can see it tracks pretty well there in both sense, temperature and humidity. So the next one was I wanted to test how they affect or how they worked in wet and dry soils, because that's kind of what we're interested in up there. So as you can see, the temperature is pretty consistent. There's not much of a difference between wet and dry soil. However, there is a very sharp difference, and you can see the fluctuation in the dry soil a little bit more pronounced. Whereas when it's in very wet soil, we kind of just pin it to its maximum. The next test that I did was to see the responsiveness of these sensors. So 2 sensors were placed in wet soil, while the other 2 were placed in soil that had been baked out to completely remove any moisture in them. I let them sit for 2 hours and then immediately switched the dry sensors into the wet to see how, or the wet into the dry to see how well they would actually like adjust to a quick change. And I found that in about 15 minutes, they were tracking very closely to the control sensors. So that showed that the response is good. We'd be able to see it happen quickly. The next thing is the depth. We're only interested in sort of just underneath the surface in these high environments like that. So the sensors are going to be placed at about 1-inch depths. So I just wanted to sort of get a baseline to see how they respond at different depths. As you can see, the surface and the humidity is a little bit more pronounced. You can see the fluctuation as the days go on. At 1 inch, that does track that fairly well. There is a little bit of a delay as it propagates down into the ground, and the same with temperature. You can see that there's sort of a time shift in how that temperature change propagates down. But it was heartening to see that at 1 inch, we can track temperature and humidity at the surface fairly well. So this is still an ongoing project. Right now, the board is consuming too much power. There's no connection, an oversight, there's no connection between the microcontroller's pin and the sleep pin on the rock block, which means that when we boot it up, it's constantly idling on and causing a big power draw, which is a big problem for the long-term viability of the sensor. So right now I'm currently working on sort of a software workaround where I'm going to try to just completely shut down the regulator from the microcontroller. I don't know how that will affect the ability of the rock block to send if it's on a constant on-off cycling instead of sleep. But yeah, still a work in progress, so we're going there. There's also been some current leakage issues that we've had. So we're going to try to implement optocouplers to where the physical electrical lines are isolated from each other, so we don't have current leaking, but can still control different pins. As I was saying earlier, big limitation of the rock block system using the Iridium satellite network is that the messages are very short. And right now, the way that our sensors take a sample is it puts on a timestamp and then temperature and humidity for 4 sensors. So it's a pretty verbose reading every time. And I'm working on sort of an encoding system right now to try to reduce it down to at least less than 20 bytes so that we could send once a day and get capture most of the day's data.
1 minute.
Thank you. So yeah, just acknowledgements from the ESIP community, NASA, NOAA, and the USGS. And I'd also like to thank the Electrical Engineering Department and Biological Sciences Department at Tech. They've been very helpful in progressing on this. If you have any questions about this, you can contact me at my email address right there. I'll also be presenting this as well as a poster during the research showcase on Wednesday. Thank you.
All right. Thank you very much, Justin. Good job. We have time for a question for Justin. Does anybody have a question for him?
In the chat, Mike Daniels asked, how much are the Iridium charges per 50 bytes?
I believe it's 20 cents per, or maybe, I think it's about 20 cents per message. I think 50 bytes is about 4 cents. But when you're sending, you know, a message every day, it'd add up really quick.
Okay, thanks, Justin. Yeah, watch the chat for more questions.
Sure
Really
thing.
glad to see that project proceeding. Looks like you've got some good results.
Thank you.
Yeah. All right, our next speaker in the flash session is Daniel Fuca from Virginia Tech. So Daniel, it's all yours. Okay, you're on mute if you're talking.
Unmute. There we go. These were excellent lead-ins to my presentation. Thank you very much for doing pretty much my entire introduction. What I do want to cover today is ultra-low power LoRa embedded microcontrollers to really simplify eco-enviro sensing designs. This is a collaborative project heavily in Virginia Tech with Morehead State included, and a new collaboration with USDA ARS, though, John, we need to probably work together too. So going on, no, let's see, a quick review of our project. I'm gonna cover an exciting new project, an accidental benchmark, and getting you started in 10 minutes and $30. So very quickly, the background is we get to use the Virginia Tech Smart Farm Innovation Network. It's all of the Virginia Tech agricultural research experiment stations around the state. And it's a bunch of hydrologists, animal scientists, electrical engineers with an open question: what can we do together for nearly nothing? Thankfully, that has changed. But what we did for nearly nothing was we were able to build a series of sensors, and we're going to focus on this red dot up here. The rest of the dots are horses running around the fields. This little dot here doesn't actually move. And that's one that we're very excited about today, because it's one of our lead efforts of cheap self-sustaining weather stations. What we're trying to do is see how close we can come to this right here, a $25,000 weather station, with this over here, which is going to be right around $30. So obviously $30 is not going to be the quality of $25,000, but we can get almost 1,000 of them into place. So our general hurdles so far have been processing, though we covered this with artificial intelligence event recognition back in ESIP 2020. The communication costs, we've cut that down a lot, and we've been we've been talking about LoRa quite a bit, and I have, we are now LoRa to cell solution for really cheap at about $5 per month. Funding, we'll cover because that's an exciting part. In power, we're going to be really is the focus of today, as well as development time. There's some trade-offs there. So our partnership and that has given us a little bit more money, plus a lot more opportunity, is with the newly formed the USDA Agricultural Research Service. And that is their new formed group called PDI, which is Partnerships for Data Innovation. It was established in 2019. It's ARS, as well as private sector tech companies, university, and industry combined. They initially are a cloud-based infrastructure with Microsoft and ESRI joining forces to provide an ARS platform. So what it opens up to us is 90 different locations, 90 different research sites, and 137 work sites around the United States. So I want to get into an accidental benchmark. This is going to be a little bit funny because those of you who know me know I'm a dog person, not a cat person. But I just want to give you this scenario. A scene set up late last August, and I'm really into cheap sensors, and there's these nice little Dragino LoRaWAN weather leak detectors, and they send information, obviously, over LoRa whenever there is a leak or a door opening. So these are things that are actively monitored and sending information. But what happened was a little bit interesting. First off, let me just explain that once I got excited about this, Dragino decided they wouldn't help us actually determine how to use plain Jane LoRa, single channel LoRa. These are pre-programmed for LoRaWAN. So I'm just going to talk about Hopita. Hopita is the cat over on the left-hand side who likes to sleep on my electronics in the winter. But as spring came, and more recently, Hopita uncovered this thing that started flashing in my bedroom in the middle of the night. It's like, what the hell are those lights? What the heck is actually going on with those lights? And it turns out I completely forgot about these sensors, and they've been reporting ever since last August. That's a very long time to be reporting. They're still reporting. So how can this actually be a LoRa sensor that stays in communication for a very long time on a coin battery? Now, I looked at my logs of the router, and lo and behold, I was actually receiving chirps from it. So they were actually getting received in those random events where the channel was the correct channel. So what I looked at was on the inside of this board, just to the lower right is the MCU, which I had to look with a magnifying glass to see that it's an ASR 6502. Very exciting. I now know what a processor is, and I can go through and start, oh crap, Google's no help. It turns out that for some reason, they're keeping this one chip very, very well, confidential. So it turns out a little bit more research shows that they have this ASR 6501 and 6502, which just happens to be a MCU with the SX1262 chip embedded. And we know that there's a sensor that sells for roughly $15 that utilizes this. So we now are talking about a price range that I can afford. So what is the embedded MCU plus LoRa? I kept on searching and searching just for that chipset, and I ended up at the Heltec, which those of you that are LoRa geeks are probably familiar with the site, and you might be a little bit excited. But now it's a little bit expensive for me, but this does also have GPS, low power, GPS, and LoRa all on one chip, which will save me in the future. If you're interested in trying to get a little bit cheaper, you can get the chipset already set up with a nice little antenna port for $9 to $15. If you want the breakout board, $15. And if you want a cute little implementation, they actually have little solar panels on these that go. And it's like, wow, that's a tiny solar panel. That's good. This is kind of good evidence that this might work. So the development time, what we have is with LoRa, I no longer have to solder on 16 welds. I don't have to solder on 8 wires on 2 different sides. I don't have to deal with the GPS soldering. It's all on this chip. And it's I2C with good pinouts. So I can plug in a lot of stuff. It also has a solar charge controller. Now remember, and we're going to go back to that little design. Remember over here on the right-hand side, I have this nice little solar unit that I stole from a light bulb, one of those nice little $3 light bulbs that I want to use to power my weather station. So benchmarking, full throttle, just wanted to see what it burns if I just keep on chirping over and over and over. Continuous chirping, the looping of the chirping, GPS and weather data from BME 280, full throttle, 160 milliamps, and that's a lot of power, as you guys know. At idle, when it's turned on, 60 milliamps, but at low power, it really, you can't even notice it. It's in the couple of microamps, and I've been testing it. If you guys remember previous presentations, I take advantage of vapors in gas stations, because a lot of gas stations will give you free or 50-cent batteries that are really nice, probably $10 battery with charge controller in there for about 50 cents to $1, because they're trying to get you addicted to the juice. That being said, I'm addicted to sensors, and this also works there too. So I'm throwing that in. I throw in the $2.50 power solution, which also includes a battery for free. And it's more than enough to just keep this system going, at least for the 2 to 3 weeks that I've been playing with it. But with the battery alone, we have about a week, and it still hasn't died with this 350 milliamp battery. So I just wanted to go with that. Basically, with this solution, you are looking at, you can actually start up with this one chip, start doing LoRa and GPS and I2C sensing in a matter of 10 minutes, and get it out and put out into the environment. It's actually fairly sweet and probably the quickest solution I have encountered. Now, I do want to say goodbye to my dear barks, but ending on good news, we have a replacement, and so we're going to welcome Ensign Tilly to fill Bark's footprints. So with that, I'm just going to say this dog is now censored for just about $30, just under $30, and now we are going on walks. And I think that is the end of the presentation. Yes.
Okay, thanks, Dan. Great job. And looks like you've got a new field buddy there, so you should have fun. Yep. All right. Well, we only got a couple minutes left, so we came in right underneath. Are there any? Is there one question for Dan? Do we have a minute for one question? So we'll take one.
I have a quick question.
Sure.
Hi, Dan. Yeah, Dan, how is your communications when you send it back over your power budget impacted by comms?
How is the communication for LoRa?
Yeah, for LoRa.
Okay, so LoRa, we are getting out of the with just soldering on a free piece of wire onto the LoRa. We're getting 1 kilometer, fairly reliable line of sight. And so what we do is we on these chipsets, we now are going into the pricier thing. So we're our first tests are seeing 2 to 4 kilometers line of sight, and then I put it and then I am coupling it to a LoRa receiver that also then spits out to a cell uplink. Both I think it's a $10 board, and for that I'm paying $5 per month to communicate all of the data through. I think it's US Mobile. I hate to sell anything, but you can get a per byte or per very, very, very cheap monthly plan from US Mobile that works well with the cellular uplinks. So LoRa to a concentrator to a cellular uplink for less than $50.
Nice, thank you.
Okay, let's thank all of our speakers one last time, especially Caitlin and Christelle for coming in and giving the longer invited talks. We really appreciate you folks making the time and educating us on what it is that we're doing that's innovative. So looking forward to more engagement on our cluster meetings going forward over the next year on some of these issues. And I would like to thank Stephanie, John, Justin, and Daniel for their flash talks. You guys did great. A lot of information in a short time. So myself and co-chairs, Renee and Joseph and Christina, say thank you to the audience, all of you for coming. We really appreciate it. And we're out of time. So check us out on the ESIP EnviroSensing email list or ESIP Slack, or just hit us up by email. We'd love to hear from you.
Thanks, Scotty.
I think we're done.
Thanks for hosting, Scotty. That was great.
Thank you.
Thanks, Bar and Susan. Looks like Susan was here as well. ESIP for hosting.